But you can do it. You guys are awesome. Okay, so we are looking at 2-5 for a second because we're going to use this today a lot. So use synthetic division and the given factor to completely factor each polynomial. So if we take this polynomial on 21 and we use synthetic division, won't we be dividing this polynomial by this? And wouldn't that take it from a cubic to a degree 2? Because 3 divided by 1 is 2, correct? And then we would know how to factor a quadratic. So what we would do is say, okay, we can do that. We're going to do synthetic division. So we know that this is one of the factors. That means we'll multiply to be it, correct? And since this is a factor, don't we know the remainder will be 0, everybody? Okay, so we're going to use -5. We put our coefficients in front. So that's a 1, a 3, a -13, and a -15. Notice it went from 3 to 1, and then constant. We weren't missing anything, so we didn't need to put zeros in. Then remember, this is the hardest part for a lot of people. You literally just drop whatever that is straight down. That's going to be your first answer. So 1, now we'll multiply up. 1 times -5 is -5. We add straight down. We get -2, correct? -2 times -5 is +10. We add straight down and get -3. Is everybody good? -3 times -5 is +15. We add straight down and get 0. We better get 0. We were told this was a factor, so our remainder is 0. So isn't this our remainder, our constant, x squared? Then we work backwards. X squared, then an x, then a constant remainder. So the new polynomial was 1x squared minus 2x minus 3, and the remainder was 0. So it says use this to factor it completely. So now don't we know that x plus 5 was a factor, and now don't we just need to factor this piece? Right? Well, multiplies to be -3 and adds up to be -2. 1 times 3, won't it be a -3 +1? So then we can quick factor this because look, our a value is +1. So this piece factors to be x plus 1, correct? Times x minus 3. So now don't we have it factored completely? And now do you see how we could solve it if we wanted? Does that make sense, everybody? Okay, any questions on that? But it did just say factor it completely, so we've done that. Okay. So try problem 22. Hurry, quickly. A couple of things. Everybody pay attention so I can kind of put it all together for you. So recall, when doing synthetic division, you get a remainder of 0. That means the polynomial is divided evenly, and this means it was a factor of the polynomial. So if I took this polynomial and I said on number 7, for example, and we've already done number 7. Just look at number 7 on 2-5. It says determine whether each binomial is a factor. So we did synthetic division using -4, correct? We got a remainder of 0, so we knew that this x plus 4 was truly a factor, meaning it truly multiplied to be it evenly. Yes. Okay, awesome. So we all get that. Awesome. Okay, so a couple things. Recall, this is everything we've learned so far when finding zeros. So we've learned how to find the zeros of many different types of polynomials. Remember that the goal is to always get it down to linear or quadratic. When I say find the zeros, doesn't that just mean solve it, guys? Yeah. Okay. So if we saw something like this on the test and I said find the zeros, isn't it already linear and quadratic? Yeah. We wouldn't miss it. We would just set each of those equal to 0 and solve, correct? We wouldn't start multiplying it out if I said find the zeros. Does everybody understand? Okay, so once again, we would set them equal to 0, and then we would solve by factoring. So when we get x is equal to -2, and then we'd factor that if possible, and solve it by factoring. I'm not going to finish doing that. If we saw something like this on the test, and I said find the zeros, wouldn't you first factor out a greatest common factor of x? Now look, we have a linear and a quadratic. Yes?
Whatever the degree is, that's something.
Yes, so this one will have 2 and then 3, correct? Because that's 1. So this would have 3 solutions. Good point. That's one thing you should always check. This one should have 3, correct? Now look, we factored out an x and left was this. So now don't we set each of those equal to 0? So then wouldn't we try to once again factor this and solve by factoring? And it does factor. So looking at this one, isn't it? So we should have 3 solutions here, and we will, because the quadratic will have 2, correct? 0 would be an answer, and then the 2 others. Is everybody good? So on the test, if you saw something like this, and I said find the zeros, you'd have to say to yourself, uh-oh, there's nothing in common. Yeah, there's 4 terms. You're getting way better at seeing that. Isn't there 4 terms? That's when we try factoring by grouping. So let's make sure it does factor by grouping. We pull out x squared, left would be x plus 2, correct? Right here we pull out a positive 4, left is x plus 2, and then we factor out x plus 2, and left is x squared, oh I already did it over there, x squared plus 4. So now wouldn't we set each of those equal to 0 and solve? And we would just subtract 4, wouldn't we? So we'll have x is equal to negative 2, and then we would have x squared is equal to negative 4, so wouldn't we square root it? And we would get x is equal to plus and minus 2i. We have 1, 2, 3 solutions. It was degree 3. We know we have them all. Okay, just making sure, because like I said, it's a lot to test on. If I saw something like this on the test, and I have the test, I wrote it myself just over the weekend, made copies. If I said to you solve, find the zeros. If you saw something like this, you would not just add 1 square cube root it, correct? That would be like the big common mistake. You'd say to yourself, I remember if there's 2 perfect cubes, we've got to factor it, correct? So this is the front and the back thing. So the front thing would be x, the back thing would be 1. Then we would factor to be x minus 1, correct? Front with the front would be x squared. Front with the back would be 1x. Back with the back would be 1. Now if this sign's minus, this sign's positive, this sign's positive. Now look, linear, quadratic. So do you see how all of them get down to linear and quadratic somehow, and then we just solve it? So this one we would use quadratic formula, but only because it doesn't factor. And this one we would get x is equal to 1. So we'll get 2 solutions from the quadratic formula. We will get 1 there. That's 3 total. Something like this, we would do a u substitution. Look, x squared squared, correct? Everybody? And then an x squared and then a constant. That's a u substitution. So we would solve for u, correct, by factoring. And then we would set x squared equal to u. So everybody remember u substitution. Okay, so now if all of those methods won't work, if you can't use any of those methods, you revert to the last method, which is today's lesson. Okay, so today is 2-6. It's the rational root and conjugate root theorem. So let's say that you get to solving something and there's no way to solve it by any of those methods we just looked at. Then you can use the rational root theorem. Now understand, you can actually always use the rational root theorem. It's just the hardest way, the most tedious way. So it's always our last resort. Did you all hear that? Yes. The last resort. Okay. So first of all, we're going to be doing rational root and conjugate root theorem. We're going to focus in on the rational root theorem first. So just some vocabulary. Rational means can be written as a fraction. If you understand what rational root theorem means, it's going to make more sense. So rational means can be written as a fraction. So everybody, all of these are rationals. Isn't 2/3 a fraction? 1/6 is a fraction. It's a rational then. Isn't -4 technically a fraction? Isn't that just -4 over 1? So that's a rational. That's a rational and that's a rational. Do you all see what rational means? Okay. Root means the root of a polynomial is the solution. So it can be real or imaginary. So if I say find the roots, I'm just meaning solve it. Period, end of story. Does everybody understand? Real roots, if you have real roots, they will cross the x-axis. So real roots are solutions that cross the x-axis. Is everybody good with that? Yep. Real crosses the x-axis. And then rational real roots. So if it was rational, does not mean it's a fraction. If it's real, does not mean it crosses the x-axis. So a rational real means a fraction that crosses the x-axis. And that's what we're learning about today. Fractional solutions that cross the x-axis. Okay, so here's the rational root theorem. We're just going to get started right away with it. So if you need to take a picture of it or whatever, this video is posted. So right now it's not going to make sense until we actually practice it. But you're going to want to pay attention here. So polynomials can only have exactly p over q possible rational roots. That's the rational root theorem. So every polynomial, as long as, so every polynomial will have only p over q rational roots. Exactly p over q. Those exact rational roots possible. So first of all, you're not going to understand what it means till we practice it. But here's the thing. P is going to be the constant coefficient. Do you see how in this example, -4 is the constant? That's going to be what we're going to call P. Okay, everybody? Now your leading coefficient is going to be Q. So you're only going to look at the 2. So that's going to be Q. Now, once again, P has to be, to use the rational root theorem, P has to be a constant, and then the Q will be the leading term. Does everybody understand where P and Q come from? Now, what we're going to do is we're going to list out factors of P. Remember, factors mean what multiply to BP. So our factors of 4 plus or minus 1, and we have to list out the positive or negative factors. We don't know if it's positive or negative. Does that make sense? So what are factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4, correct? Okay, so those are the possible factors of P. Then we'll list out factors of Q. So what are possible factors of 2? Plus or minus 1, plus or minus 2. So now the only possible rational roots, meaning if it crosses the x-axis and can be written as a fraction, it's going to be one of the combinations of P over Q. So we're going to take and do P divided by Q, all possible P over Q's. So let's start with these P's. 1 over 1, isn't that 1? Yeah. So plus or minus 1 is an option. Let's do 1 over 2. A half is an option. Does everybody see how I'm listing out possible rational roots? So it's really not that hard. 2 over 1, that's P over Q. So won't that be 2? So 2 plus or minus 2 is a possibility. And then 2 over 2 is 1. Haven't we already listed 1? And then 4 over 1, so that's a possibility. And then 4 over 2 is 2. Haven't we already listed that? So guys, it's really not that hard. The only possible rational roots of this polynomial are these. These are the only possible rational roots. Only those. Those would be the possible rational roots, meaning if it's crossing the x-axis for this polynomial and we can write it as a fraction, it's going to be one of these solutions. Does everybody understand? So then from there we would go through and we would test them to see which ones are actually rational roots. So yeah, these are all the possibilities, and then we'll go through using synthetic division and test each one of them. When the remainder comes out 0, we know it's a root. Cool. Okay, so this would be our last option, like only if we're desperate. Okay, so here we go. Let's just start practicing. So let's do number 3. Here we go, guys. It's a lot easier than it looks sometimes. Okay, here we go. So it says use the rational root theorem. Now here's why. Everybody look at this polynomial. Do you see how there's nothing in common? And there's 4 terms. If we try factoring by grouping, which is what we would do on the test, so there's 4 terms, so we try factoring by grouping. But do you see how it won't factor by grouping? So that's when you know I've got to use the rational root theorem. So what we're going to do is say, okay, this is my Q, this is my P. Is everybody good with that? The constant's always P, the leading term's always Q. Now we're going to list out factors of 1. What are some factors of 1? Plus or minus 1. Does everybody feel good? Now let's list out factors of Q. So plus or minus 1, plus or minus 2. So now we're going to list out all possible P divided by Q's. These are the possible rational roots, the only ones. So guys, doesn't that make sense on how really there's not that many? These are the only possible ones that we're going to cross the x-axis. Okay, so 1 over 1 is 1, and then 1 over 2, right? That's it, correct? Yeah. So do you see how there's only 4 possible rational roots here? Not that many, correct? So these are the possible rational roots. Does everybody feel good? Okay, now, those are the possible rational roots. So we've answered the first question. It says, use the rational root term to list out all possible rational roots. Now it says, find any actual rational roots. So what we're going to do is, let's start with positive 1. Let's set up our synthetic division, and let's go through this and see if the remainder is 0. So we're going to have a 2, a 5, a 4, and a 1. Okay, we drop down 2. 2 times 1 is 2. We add straight down is 7. 7 times 1 is 7. Add straight down is 11 times 1 is 11. We add straight down and get 12. Now look, the remainder, that's always our remainder. The remainder is not 0, so we know that 1 is not a solution. It was a possibility, but it's not a solution. So let's try negative 1. Okay? So negative 1, I'm just going to draw this in again. We do 2, 5, 4, 1. Let's go for negative 1. We drop down 2. 2 times negative 1 is negative 2. We add straight down and get 3 times negative 1. Negative 3. We add straight down and get 1. 1 times negative 1 is negative 1, and we add straight down and get 0. Yay! We know this was a solution, correct? So that's an actual rational root. Now what I want you to think about, we're not going to keep testing at this point. Here's why. Maybe a half is an answer, maybe negative a half is an answer. Let's check it a different way. So now didn't we go from a cubic to a quadratic? So this is 2x squared, right? Guys?
Yeah.
Plus 3x plus 1. Does everybody understand that? If this factors, now think about it. Anything that factors, can't you solve it by setting it equal to 0? And aren't they always written as fractions? Right? Think about it. You have x minus 2 times x plus 3 when you get 2 and 3. If you have 4x plus 5 times, you have 4x plus 5 times 3x minus 2. You see how you would get negative 5/4. So do you see how, and you would get 2/3. So do you see how if it's factorable, then we have more rational roots? Does everybody understand? So if it's not factorable, we'd have to use the quadratic formula to solve. And that would be imaginary or irrational. That's the only time we use quadratic formula. So let's see, does this one factor? Well, it multiplies to be 2 and adds up to be 3. 1 times 2. So it does factor. So there's going to be more rational roots. So let's solve for the other 2 rational roots by factoring. But aren't they going to definitely be 1/2 and negative a half? Because those are the only other 2 possibilities. But do you understand if there were more possibilities, we'd just solve by factoring? So do you want me to continue, or are you good with saying, since we know that those are the only other 2 possibilities, we'll just go with those? Do you want to continue?
Yeah.
Okay, let's factor it. So let's continue solving. So don't we drop and break?
Yeah.
So we drop down 2x squared, we drop down positive 1. Then we're breaking down the middle term, which we said was positive 1x and positive 2x. So I'm going to do plus 2x plus 1x. Okay, awesome. Oh, yeah, it's a good thing we continued to solve because I would have been wrong. So what's in common here? 2x, and left would be x plus 1. What's in common here? We'll factor out a 1, and left is x plus 1, correct? So now let's keep factoring out an x plus 1. Left is 2x plus 1, correct? So now set each of those equal to 0. So when we get x is equal to negative 1, didn't we already have that as a solution? So that would be x equals negative 1 with a multiplicity of 2. Does everybody understand? We got a negative 1 again. Didn't we already get that from synthetic division? Okay? And then we also get x is equal to, what did we subtract 1, divide by 2, guys? Negative 1/2. So our other solution was x is equal to negative 1/2. So this was our final answer. So do you see how if we would have just assumed and went positive 1/2, we would have been wrong? Okay. We have 1, 2, 3 solutions. Was it degree 3? Yes.
For sure, for sure.
The negative 1 with a multiplicity of 2, because we got that before we had the quadratic. Then the quadratic gave us another solution. Now I want you to pull up your graphing calculator. Type that in. So let's all type that in, number 3. And look, you can see that it does truly cross the x-axis at those exact places, and only those places. But since it's crossing at negative 1 with a multiplicity of 2, won't it bounce at negative 1? Guys? Okay. So graph it on your graphing calculator real quick. Anyways, I don't want to take the time to do that, but you could graph it on your graphing calculator to see that it truly does bounce at negative 1. Does it bounce at negative 1? Let me see. You guys type it in. I don't have time. The original function, guys, right? Graph it and we'll see where it crosses the x-axis. You need to make your window smaller. Make your window small so you can get in there really close to those zeros. Aren't our zeros between, like, really small right here? Like, they're not that big. So make your x max and x min small. Do you want me to type it in? So it bounces at negative 1, and then does it cross at positive 1/2 again? Your window's probably not small enough to see it. It's not. It is? So you made your window like really small, maybe like -2 and 2 for x min and max, and then you can see it probably. Your y I'd make smaller too. Okay, everybody good?
Yeah.
Okay. Let's do another one. Here we go. Number 1. Okay, everybody brace yourselves. Here we go. So I need everybody ready to participate because this one's going to probably take us till lunch if we don't all participate. Here we go. So we'd say to ourselves, can we solve any easier method? No. So that means we're going to use the rational root theorem. So we have a constant and a leading term so we can use it. This is our Q, correct? This is our P. P is the coefficient, correct? It's the other way around. So if I did that on the test, which is the most common mistake, as you can see, it's easy to do, we would get it wrong. This is Q, this is P. Glad you caught that. So plus or minus all factors of 15. 1, plus or minus 3. We're listing out factors of 15. 5 and 15, correct? Now Q, plus or minus 1. So won't all possible P over Q's be everything divided by 1? So we're just going to have plus or minus 1 is a possibility, plus or minus 3, plus or minus 5, plus or minus 15. These are the only possible rational roots. So we've listed out possible. That was part of our answer. Now we're going to find the actual. So what we're going to do is synthetic division with all of these. And then if any of them come out, then we would say yes. If none of them come out, we would say no. No. So, can I be honest? Okay, this is number 1. Okay, so we would test this. So can I be honest with you for a minute? We would go like this, right? We'd put a 1, we would test it out, right? Using our leading coefficients. Then we would test out -1. Then we test out 3. We test out -3. We test 5. Then -5. 15, -15. None of them come out with a remainder of 0. So we would have no rational roots. Yes. So none of these come out with a remainder of 0. So I don't want to waste your time. Like, do you guys understand what I'm saying? If so, we're good. I would test all of these. And this would be my last resort, right, on the test. But do you see how none of these came? You didn't see, but I'm telling you, if we did synthetic division with all of these, none of them have a remainder of 0. So we'd say no actual rational roots.
Yeah.
I mean, that's just true, right? There's no actual rational roots. These were the possibilities. There wasn't any actual one. Now, that means that we must have irrational or imaginary solutions, correct? Irrational means can't be written as a fraction, like the square root of 3. Does that make sense, everybody? Is everybody feeling pretty good about this? It just takes a little bit of practice. Okay, let's do maybe, I picked all the hard ones. Yours will be a lot easier. So do you want to do maybe this one, list out possibilities? Yes? Okay, here we go. Okay, so there's no other way to solve this besides P over Q. So here's our P, here's our Q. Okay, so listing out factors of P, plus or minus 1, plus or minus 2, correct? Plus or minus 4. Does everybody understand? Q is plus or minus 1. There's a lot here. What multiplies to be 36? We don't want to miss anything. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus
4.
Nope.
36 doesn't 4 like that.
Uh-oh. Yep, 4 plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18. I think we've got them all, right? And plus and minus 36. Yep. Now all possible P over Q's. This was a really hard one. So 1 divided by all of those, correct?
So we only have to do some synthetic division.
No, 1. So you have to do
9,
more.
and then
9
plus or
times
minus.
2, 18 times.
Yeah. You only have to do it.
No, you wouldn't. You don't do it till you find 1, and then that's why we're doing this. And then you would use quadratic formula, or not quadratic. If it factors, you're good. Okay, so we're doing 1 divided by all those things, right? We're not going to forget. So we have 1 over 1. Then what we have 1/2, 1/3, 1/4, 1/6, 1/9, 1/12, 1/18, and 1/36. Okay, let's list those out. So 1/2, 1/3, plus or minus 1/4, plus or minus 1/6, plus or minus 1/9, plus or minus 1/12, plus or minus 1/18 is a possibility, plus or minus 1/36. Me too. Okay, so now we got to do 2 over 1, 2 over 1, right, which is 2, plus or minus 2. But then look, 2 over 2 is 1. We've already listed it, right? 2 over 3 is not a possibility, plus or minus 2/3. 2/4 is 1/2. Don't we already have that listed? 2/4, 2/6, 1/3, we're good. 2/9, we gotta list that. 2/12 is 1/6. 2/18, 1/9, right? 2 over 36 is 1/18. We've already listed that. Now we'll do 4 over 1 plus or minus 4. That's 2 over 9. Sorry. And then we have 4/2 is 2. We've already listed it. 4/3. And then we would do 4/6, 4/9. We need that one, right? There is going to be one, but not probably this card. Then 4/12, 4/18, and 4/16 we've already listed. Okay, these are the possible rational roots. Now, if there's ever one this big, let's cheat using our calculator. So type it in honors of we would not let you cheat. And on number 2, type in 36x cubed plus 144x squared minus x minus 4. Everybody type it in. So really, it's not that bad. Type it in. Type it into the graph. Go to y equals. I'll do this one so I can make sure we all understand what I'm talking about. So we'll type in 36x raised to the 3rd, and then plus 144x squared minus x minus 4. Now we're going to hit graph, and I'll see if I need to change my window. I'm going to look at what my window is. So I'm going to just do a standard viewing window and then see where I need to go from there. So -10 and 10, -10 and 10. Okay, let's graph it. So, hey, look, it's crossing at some really big decimals, right? But then, don't we know it's crossing at -4? So what would our answer be? One of them. -4. So won't we use synthetic division with -4? And then get it down to quadratic and then solve it by factoring. Remember, we know what the graph looked like, so it's down and up, right? Because it's a cubic. Down and up. Right. So down and up. And so, yeah, it's not a very pretty picture. But can't you see that it crosses at -4, everybody? Yeah. So when we were testing these with synthetic division, we would have got -4 gets a remainder 0. So let's use -4, guys. Let's do synthetic division. Here we go. We put in 36, we put 144, we put -1 and -4. We weren't missing anything, correct? 3, 2, 1, constant. We drop this down exactly as it is. So somebody tell me what this is. 36 times -4. Negative what? 144? We add straight down and get 0. 0 times -4 is 0, correct? We add straight down and get -1. -1 times -4 is 4. We add straight down and get 0. So, which makes sense, right? We already knew that, though. Right? -4 is a solution. Now look, didn't it go from a cubic to a quadratic, everybody? So this is 36x squared and then -1 equals 0. Now we know how to solve that easily. Let's just solve that for the other rationals. Wouldn't we just set it equal to 0 and solve? So what do we add 1? So we have 36x squared is equal to 1. We'll divide by 36. Now we would square root it, correct? So isn't that the square root of 1 is? 1. The square root of 36 is? So our other two solutions that were possible was plus and minus 1/6, which we found are actual rational roots. So we found all 3. But do you see how we used our calculator to cheat to find one easy one, a whole number 1, and then we did that. Does that make sense? Questions? Are we all feeling okay? It's really not that bad, especially if you have a calculator, you can graph it and kind of cheat and know where to start with. So if I let you do that, I don't want to have little baby crying. Little baby's crying. Okay? I would find a whole number root, like we did, then do synthetic division, and then solve it by factoring or something like that. Yeah, let's say across that 1 and -4. Go with 1, divide it down, and then do the rest though by factoring.
So when it says then find any actual.
That's what we were doing, right?
Yeah.
We listed out the possibilities, and then the actuals on this one were 4, right? Out of all those possibilities, the actual one was positive 4, correct? And then wasn't it plus and minus 6? Do you see what I mean?
But. So basically when it asks.
R was negative for you.
The actual rational root is basically same as 0.
Yeah, no, yeah. These are the possible rational roots. We're finding the actual ones, the ones that does cross. Okay, so do 1 through 16, ready, set, go. Yes. Okay, everybody, look up here. Okay, here we go. So number 16, it says, use the rational root theorem to list all possible rational roots, then find any actual rational roots. So this is going to be a certain part on the test. So I'm going to say this exact thing. So we'd say, okay, the rational root theorem. This is my Q, correct? This is my, nope, that's my P. I keep doing that in this class only for some reason. That's my P, correct? My Q is 1, correct?
Yep.
So then we'll list out all possible P's, factors of P. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Those are the possible P's. Q is plus or minus 1. So all P over Q's are the only possible rational roots. If it crosses the x-axis and it can be written as a fraction, it's in one of these spots. So anything divided by 1 is just itself. So we have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Does everybody understand? So this would be part of our answer. These are the possible rational roots. Now, because we're not in honors, I'm okay with you pulling up your calculator to get some values that maybe you can expect or suspect to work. So look, if you graph that into your graphing calculator, go to y equals, type in x cubed plus x plus 10. You hit graph. Do you see how it looks like it's crossing at -2?
Yeah.
We're not going to assume it's definitely -2. We're going to test it with synthetic division. So instead of testing all of them, I'm okay, since this isn't honors, to kind of use your calculator. So we're suspecting it's -2, so we'll set up synthetic division. Let's test it. Now careful, careful. Isn't it missing x squared, guys?
Yeah.
0. So we have a 1 x cubed, then a 0 x squared, then a 1x, then a 10. If we miss that, we will mess up on the whole thing. So now we would drop down this, whatever it is. So there's a 1. 1 times -2 is -2. We add straight down and get -2. -2 times -2 is +4. We add straight down and get
It works.
5.
It works.
5 times -2 is -10. We add straight down and get 0. So our remainder was 0. So we know that x does equal -2. It is a solution. Okay. So then, everybody, we got to continue. Didn't we go from, let's look though, we got to make sure we went from a cubic degree 3, we divided by 1 root, so we are now at a quadratic, right? So we have x squared minus 2x plus 5. Now let's see if that factors. If it does factor, guys, there are 2 more rational roots. Do you all understand that?
Yeah.
We would just solve by then setting them equal to 0. If it doesn't factor, this is the only rational root, because then we would have either irrational or imaginary, correct? So what multiplies to be 5 and adds up to be -2? Nothing, right? So do you guys all understand that it's not factorable? So that means there are no other rational roots. Now that makes sense. Look at your graph. Doesn't it never cross the x-axis again? So that means the other 2 solutions must be imaginary. Now tomorrow, I would say solve it. So wouldn't we just use quadratic formula to continue solving it? Does that make sense? Today we're stopping though. That's our only rational root. These were the possibilities, but this is our only actual rational. So do you see how it's pretty easy, especially if I allow you to use your calculator to get a suspected value? Okay, yes. No, it has 3 solutions, because the other 2 we would have to solve by quadratic formula. So tomorrow we'll continue. Like tomorrow it's the same thing, but I'm saying find any. Does that make sense? Tomorrow or next time. Okay. So you guys will understand that just because of the wording, it said what are the actual rationals. This is the only actual rational. The other 2 must be imaginary or irrational, but we knew they were imaginary in this one. Yeah, but in the instructions and on the test, it just depends on what it asks. So in the instructions, it says use the rational root theorem to list all possible rational roots. So we've done that. Then it says, then find any actual rational roots. So this is the only actual rational root. So we've answered both questions. You have to have both to get them right on the test. Okay. Sweet. Okay, I'm going to let you continue practicing. Well, there's the next thing. Everybody listen very carefully. This is really important. The conjugate root theorem. So the conjugate root theorem says if you have an irrational root, meaning can't be written as a fraction, or imaginary root, then their conjugate must also be a root. So conjugate pairs are, if you have imaginary solutions or irrational solutions, their conjugate has to be a solution. They only come in conjugate pairs. So, irrational means cannot be written as a fraction. If you have something that's irrational as a solution, its conjugate must also be a root. So the square root of 2, do you guys all understand that that's irrational? Okay. And then 5 minus the square root of 3 is irrational. Can't be written as a fraction. This is also irrational. And then conjugate means a change of sign in between. So everybody, let's talk about let's write out the conjugate of each of these. Just look. Conjugate is only a change of sign in between the terms. So this conjugate would be 2 minus 3i. Do you all understand? The conjugate of this is still negative 4. It's just plus 2i. The conjugate of this is negative 3 minus 2i. Does everybody understand?
Yes.
Positive 4 plus the square root of 7. Negative 5 minus the square root of 3. We all see how this works. So what's the conjugate of 4i? Negative 4i. Do you see how that's 0 plus 4i? Doesn't that be 0 minus 4i? The conjugate of that is the positive square root of 3. Okay, we understand what a conjugate is. So once again, if you have an imaginary root or irrational root, its conjugate has to be a root. So if x equals 2 plus 3i, then x equals 2 minus 3i also has to be a solution. So if x equals negative 4 minus the square root of 3, then x equals negative 4 plus the square root of 3. Red flag. Students just start going with this, and they say, okay, so if x equals 5, then x has to equal negative 5. Not true. That is not true. It's only, yeah, I know, but people say that the conjugate's also a root. That's not true. But do you get what I'm saying? That the conjugate is not a root necessarily. Only for irrational or imaginary. Okay. Okay, awesome. So let's do number 17. It says, everybody, this is a little bit harder. You're going to need some paper. Now, it's only harder because there's a lot of room for error. So everybody pay attention. So it says, a polynomial function has these given roots. Find 2 additional roots. So these ones are easy. What's the other root? 2 minus 3i, correct? And negative square root of 7. So what degree would this be? How many roots are there? 3. Nope. Guys, 1, 2, 3, 4. There are 4 roots, right? So what degree would this be? 4. Because you guys understand, right, that if there's an imaginary root, its conjugate must also be a root. So what's the other root here? 3 plus the square root of 2. Are we understanding this or not? 1 minus the square root of 3 also has to be a root. Does everybody understand? So I'm going to give you a couple seconds to finish up 17 through 22. It says, a polynomial has these given roots, find 2 additional roots. We know if we have an imaginary root or irrational root, its conjugate must also be a root. Do we have those down? Okay, so everybody, let's do number 23. Now this time, in the instructions, it says, write a polynomial in standard form with these given roots. So guys, it only gave us 2 roots. So we have x is equal to negative 5, correct? We have x is equal to 3i. What else is also a root? Nope, see, you just made the common error, right? Just because this is a root does not mean that its conjugate is a root, correct?
Yeah, right.
Only imaginary roots and irrational. So what else is also a root? Negative 3i. Does everybody understand? Okay, so now we're going to work backwards. Yep, so this will be a 3rd degree. So now we're going to work backwards. If we want to put it in standard form, this is working backwards. We're going to add 5 to both sides. So we have x plus 5 equals 0. We're going to subtract 3i, So we have x minus 3i equals 0. That was the linear factor. We'd add 3i, So we have x plus 3i equals 0. Before they were split apart, they were technically multiplied together. So let's go like this. Now take my suggestion. Anytime I'm dealing with this, I'm multiplying 3 together. We know we always multiply 2 together first, correct? Now take my advice, and if you don't, I'm going to make you go back and change it because you're making it way hard on yourself. Always multiply the conjugates together first, okay? Just because it's going to make it easier. Middle terms are going to cancel out, as you're going to see. So let's multiply this out very carefully. Here we go. So we know that we're doing x times x, which is x squared, right? X times positive 3i is positive 3xi's, correct? Then negative 3i times x is negative 3xi's. Negative 3i times positive 3i, very careful. Negative 9i squared. Okay, don't our middle terms cancel out for conjugates? So we have x squared, and then we have minus 9i squared. Now we have to remember, I squared is equal to negative 1. So isn't this x squared minus 9 times negative 1? So we have x squared plus 9. Okay, awesome. And now we're going to multiply in x plus 5. So now we have one last distribution here. X times x squared is x cubed. X times positive 9 is positive 9x. 5 times x squared is positive 5x squared. Positive 5 times positive 9 is positive 45. Then we put it in standard form. So our final answer is going to be x cubed plus 5x squared plus 9x plus 45. Now, if we would have worked backwards and solved it, we would have ended up at those solutions that we have at the top. Does everybody understand how to do it? One more? Okay, number 25. Oh, this one's a nightmare. Okay, let's go through it. So it says, write a polynomial in standard form with the given root. So we have x is equal to 3i, and what else do we have? X is equal to what? Negative 3i. We have x is equal to the square root of 6, and we have x is equal to negative square root of 6. Now that's only true because they were irrational and imaginary. So now let's go backwards. Let's do it in our heads, if you don't mind. When we have x minus 3i for this one. X minus 3i. Are you sure you're okay with that? I usually don't skip, but does everybody understand? Then when we have x plus 3i. Okay? And then when we have minus the square root of 6. X minus the square root of 6. From this one, right? And then we add the square root of 6, so we'll have x plus the square root of 6. Take my suggestion. Multiply the conjugates together, Let's focus on the imaginaries. We just did one with this exact thing, right? We distributed this exact thing a second ago. Didn't we get x squared plus 9? Okay. Let's distribute this one, though, because we haven't done that before. X times x is x squared. X times positive square root of 6 is positive x square root of 6. Negative square root of 6 times x is negative x square root of 6. Careful, right? Here's where most people make errors. Negative square root of 6 times positive square root of 6. That's negative square root of 6 and 6 is 36. Yep, so these cancel out the middle terms. So that's going to be x squared minus 6. So now we're multiplying x squared minus 6. Does everybody see how I did that? Now we'll distribute that. We're almost there. X squared times x squared is x to the 4th minus 6x squared plus 9x squared minus 54. Combine like terms and put it in standard form. X to the 4th, and then we have minus plus 3x squared minus 54. Now that was the polynomial that generated those solutions. So we went backwards. So if we were solving this one, we would have done u substitution and ended up up there. Does that make sense? With plus and minus and all that? Yeah. So we're just going backwards. Are you guys okay with this? Yeah. Okay, I'm going to let you practice, but I think I'm going to have to take off a few because some are really hard. And we're not going to get to it. Okay, so you're going to do these problems. I'll tell you which ones. So you'll do 26, 27. If we've already done them, that's okay. You'll do 29. You're going to do 30. You're going to do 32 and 33. Now, I want you to look at 32 and 33 right now. You have x is equal to 4 and x is equal to 6. Are their conjugates going to be roots? No. Okay, good. Making sure. You're going to do 32, 33. You're going to do 23, 24, and 25. What the heck?
Yeah.
They were stapled backwards, right? Oh, I had my TA do that, okay. So 23, 24, and 25. Those are the ones that's required of you to do. So it's pretty much all of them, yes.
You don't need example.
No, I mean on this page. Anything else I've already asked you to do, you have to do. So you're doing the whole front page, and then those are the ones I'm requiring you from the conjugate. So basically, yeah, the only ones you aren't doing is 28 and 31, because those are, you don't know how to do those yet. You might think you might know how, but you will get it wrong.